All right, well, let's do something a little different. This section is not mandatory. You do not have to listen to it. You can just close out right now. You do not have to do it. But it is going to talk about permutation combinations, so if you don't remember how to do those, you might want to pay attention. It's also going to talk about some tree diagrams. All right? But first, I'm going to try some tres leche. All right? So, let's see how this goes. Actually, first off, I'm really bored right now. Have you guys been watching the World Championship of Chess, or did you? You should look it up. It's very exciting. It's very exciting. It's 2021. I'm assuming if I keep using these videos, but it's 2021 right now. It's very exciting. You guys should be watching it. Anywho, it's probably over when you listen to this though. All right, so tree diagrams. Here we go. So a tree diagram is essentially a way that you can display the outcomes of an experiment that has a series of events. Okay, so if you have multiple things happening in a row, you can use it as a way to just put up the information so that you can keep track of it. Okay, you can follow it along and you can see what the percentages are. So we have an example here with YouTube, and so YouTube, people watch YouTube because it's the YouTube and it's run by the Google. So 27% of adults that use the internet are between the ages of 18 and 29. Most of them are looking at the memes, looking at all you. Another 45% between 30 and 49, and then the last 28 are over 50. The study shows that 70% of those that are 18 to 29 visit YouTube, 51% for 30 to 49, and 26% if they're over the age of 50. So all them old people still looking at the YouTube. Okay, so we're going to put this in a tree diagram. It's going to look something very pretty. Look something like this. Okay. All right, so this would be an example of what it would look like. So the first one would be the breakdown of every adult. So you see the top one is the 18 to 29, 30 to 40, and then over 50. And then the numbers next to them are the percentages. So 27, 45, and 50, 28 for the 50 plus. And then after that, the next one was if they visited YouTube or they did not, and then it shows those breakdowns as well. So if we wanted to go, oh, somebody 29 to or 18 to 29 and they don't visit YouTube, you go, oh, it's 27% and then 30%. So you have them in their rows and you're able to connect them. Okay. So let's say we want to take this and we want to find probabilities for different things. So what's the probability that a random person between the ages of 18 and 29 visited YouTube? So this is if you just take somebody randomly out there out of the YouTube and for web space, the connection of all things. Okay. Now, when they are, when you have these restrictions, you just follow the path and you multiply all those probabilities. Okay. So you multiply all those probabilities together using your multiplication rule. Hold on, I lost track of my notes. Oh, right here. Okay, so probability of a random person. If a random person selected, what's the probability that they are 18 to 29 and they visited YouTube? It would be that 0.27 times 0.7, which gets us just short of 19%. Okay, so 19% chance that somebody randomly selected would be 18 to 29 and they visited the YouTube. The next one we're looking at is what's the probability that a person just in general has visited the YouTube. And now with this one, since we have 3 different options for people visiting YouTube, what we would do is that we would find each individual probability of the groups visiting YouTube. So 27 times 0.7, 0.45 times 51, 28 times 20.26, and we would add each one of those together because we'd find the probability of an 18 to 29 year old visiting YouTube, a 30 to 49 year old visiting YouTube, and 50 plus visiting the YouTube, and you add them all up and you see that half the people that would be selected visited the YouTube. Okay. So if you have multiple things that end at different branches of the tree, you would find the probability of each one and then add them up. Okay. One thing you can do with these is, as you move along, you can write next to it, write what the probability is. So you can go, oh, this probability is your 18.9, this one's this, and so on and so forth. You can find the probability of each individual, and then you just have to do your adding at the end. Okay. All right, so last one is, what is the probability that a person has visited YouTube? If you know a person has visited YouTube, what's the probability of them being between the ages of 30 and 29? So you would want to find the probability of a person that is 30 to 49 visiting YouTube. So you would do your 40.45 times 0.51, and that would be divided by the probability of all the people visiting YouTube, which was the one that we found before, which is that 0.49. Okay, and you would multiply those together and do the division, which you see, if you know somebody has visited YouTube, then there is a 46.7% chance that that person is between the ages of 30 and 49. Okay. All right, so you can still use your conditional probability on these to be able to do it. Okay. All right. If you're still here and you're still following along, the next thing on your notes that you have is another example. So you can go through that. You know, answers there are like 0.295 and 0.142, but you know, you can do that yourself. Next thing we've got is our counting principles. So the counting principles are great because you're basically just fast tracking all these branches that you're doing. So instead of counting every individual branch, you're using multiplication and different things to be able to find your answers quicker. Okay, and since you could have something that has many different options, let's say we're talking about kids in a certain grade taking a certain class at a certain time with a certain grade, that tree just starts blowing up, and you could have hundreds of different things that you're trying to pick, and none of them are going to work. So to try to fast track that, instead of having you draw out the entire diagram, we can use some of our counting principles to be able to multiply numbers together to be able to find them. Okay, so let's talk about McDonald's here. Them golden arches everybody loves. So there's 31 different sandwiches approximately at McDonald's or McDougal's. You can get a fry in 4 different sizes. I think they shrunk it down to 3 now because I don't think you can supersize anymore because of that one guy. Whatever it was. Also 4 different sizes. Drinks. Maybe they're counting kids. Okay, they might be counting kids. How many different meal options are there? Well, you would just take each one and you would multiply them, and you can find the grand total. Now, you're not finding the probability of each, but since these probabilities are all equal, you could find it. But since you're just taking every one, there are 496 total possibilities that you have. Now, the order in which you pick it didn't order. You could have ordered the fries first, and then the drink, and then the sandwich. Or you could have done drink, fries, sandwich, or sandwich, fries, drink, so on and so forth. There's so many different permutations there. Now, if we want to take something different, and then we shrink it down, and we've got 5 people, and they got to sit at a dinner table. There's 5 spots at this table for 5 people. First one there gets to pick their spot. Second one there gets the next spot, so on and so forth. To find how many possibilities that they could be seated around this, what's the possibility, or how many options are there for somebody to have the first to sit in the first spot? Well, there's 5 people that can fit in the first spot. How many can fit in the next one after the first spot's taken? 4. How many can fit in the next? 3, 2, 1, and you multiply them all together. Okay, so it would be 5 times 4 times 3 times 2 times 1, which is 120. So there's 120 different seating options for those 5 people between those, or at that dinner table. To condense this, we use the exclamation point. Okay, it's kind of like us saying 5, and we're all excited, but we call this a factorial. Okay, and basically whenever you see a factorial, what you're doing is that you're multiplying whatever that number is, you're multiplying that number and all the numbers below it all the way down to 1. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. and you'd multiply it all together. Now, these grow very, very quickly. If you have a standard TI 63 or 83, 84, you can only go up to 69 factorial. Okay, so your calculator can only say 69, and then it gives you the number. After that, it only goes to, when you type in 70 factorial, it comes up with the answer of overflow. Okay. Now, on your calculator, to be able to do this, it is under math PRB, and it's like number 4, something like that. You'll see it's fairly easy to find. One little fun fact: 0 factorial and 1 factorial both equal 1. So if you have something that's a 0 factorial, it is 1. It's not 0. Okay, so if 5 people are sitting there, but you only have 3 chairs, how many people can sit? Well, it would be 5 get the first one, 4 possibilities for the next one, 3 for the last one, 5 times 4 times 3 is 60. So since there's only 3 spots, we would only have 3 multiplications that we would do. The previous one, when we had 5 seats for 5 people, we would multiply it all the way through. But since we're stopped, we don't use them all, we have to stop at 3. Because those last 2 people are going to be standing in the corner, at a dinner party. Because that's what happens when you show up late. Show up early, kids. That's my word of advice. Now, with this, we have our permutation. Now, our permutation is where we can take something that's a larger sample and we can take only a small segment of it. So, permutation is when the order matters, okay? So, whoever is first, second, third, fourth, fifth matter in this. That's when you are using a permutation. How many ways can the top 3 people finish in a race out of 8 people? Okay, that's using a permutation because you got first, second, third. Just making a group of people, that doesn't matter the order because it doesn't matter who was first and who was last. So permutation, the order matters. And to do a permutation, you have NPR, okay, not the National Public Radio, is equal to n factorial over n minus r factorial. Now, the n should always be the larger number. So when you are doing this, n is the large sample. How many total? Previous example, 5. The r is how many you want in the smaller group. It could be 5, or it could be 3, because we want 3 out of 5 for our calculator. So if we type it into our calculator, this is how you would type it in on your TIs, okay? I don't know if this is with pretty print. So if you have nice, pretty math print, it might be a little different. But for the basic ones, this is what you would do. 5, math, PRB, NPR, and then number 3, and then you push enter. And it's going to tell you your answer of 60. And if you don't believe me, take your calculator out, turn it on. If the batteries are dead, replace the batteries. If it's not charged, unplug whatever iPad you have and plug in your calculator and figure this out. It is important. But it is going to work. Okay. Next up is we have a combination. Now, a combination is different from a permutation because combination does not matter the order. You're just looking at a group. How many combinations of this group can be formed? Okay. So if I had 5 people, but only 3 of them can be a part of the super special club, how many different ways we can do that? That is using a combination. Now, the big difference here is that the r factorial is on the bottom as well. Now, you're not going to have to do this by hand unless you forget how to do this on your calculator, which would be a problem. Okay. Now, when you're doing a combination, it is, let's say 5C3. You do 5 math, PRB, and then you look for NCR instead of NPR. So NCR, National something, whatever, radio. National Canadian Radio. Boom! Got it. All right. And then you push 3, enter. And that's going to get you 3. Now, combination, this is serious right now. So I know this has all been fun and games and everything, so this is serious. Combinations will always be equal to or less than a permutation. So if you have 2 options, you can go, okay, the combination and a permutation, these are our 2 numbers. The combination will always be the smaller of the 2 because you don't matter the order. You're just looking for groups. So a permutation should always be larger or equal. Very rarely will they be equal, but the combination will be smaller. Okay. So when you're looking at is it a combination or permutation, you want to ask, does the order of the objects matter? Is it relevant? If it is, then it's a permutation. If it's not, it's a combination. Permutation, combination is a great way to find total sample size, but it's not going to find the probability. So use permutation combinations to find sample size, not the other way around. Okay? All right. One last slide, I think. Nope, there's two. Hold on. We got to stop recording and re-record. I guess I could have tried it, but it would have been close time-wise. Anyway, that's what happens when you use the free stuff, kids. Just a little bit extra work. Okay, replacement. Replacement is when whatever has happened, you put it back, and so the probability doesn't change. So the example here is the probability of pulling 2 hearts out of a deck of cards with and without replacement. Okay, so in a deck of cards, there are 13 hearts, 13 spades, 13 clubs, and 13 diamonds. There's 13 of each. We don't have jokers in our decks because we're not jokers here. We are serious math students. You hear me? Serious students. Now, when you are doing without replacement, when that first heart is drawn, the total number of hearts now in the deck is now subtracted by 1, because instead of having 13, you're down to 12 because 1 is in your hand. You have the heart of the cards. That means the total probability, or the total sample size, also has decreased by 1. So both those numbers would fall. So it would be 13 over 52 and then 12 over 51, and you multiply it together. You see it's a 5.8%, or 0.0588. 0.0588. If you do replace it, after you take that heart out, you put it back in, shuffle the cards up, and then you draw another one. So that one could be taken again. You have a 1 out of 52 chance of drawing the same card a second time, which means its probability would remain the same. 13 over 52, 13 over 52. Multiply those together, and you see you get a slightly higher probability. Not much, but it is higher. Okay, at 6.25%, 0.062. So if there is replacement, the probabilities won't change from one to the other. If there is not replacement, the probabilities do change, so you got to watch out for that. All right. So let's do an example with and without replacement, or with and with replacement, blah, 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 blah. Anyway, so the dresser drawer, your dresser drawer, those of you that have socks in a dresser. There are 6 blue, 10 gray, and 4 black socks. And they are unpaired and mixed up because we're rebels without causes and we don't keep our socks together. I don't know, all honestly here, I don't know who doesn't match up their socks. That's just weird. Anyway, back on track. In a dark morning, basically what you do is you just pull 2 socks out, you put them on, you walk out the door. So the question is, what's the probability that the 2 socks that you grabbed are pairs? Or are you going to be having mismatch day, because we all love mismatch day. So we'd find the probability of pulling of a blue and a blue, a gray and a gray, and a black and a black. Now this is without replacement, because when you pull one sock out, you put that on your foot, and then you got to put the other sock on, so you don't replace that sock. So that means this is without replacement. So the blue would be 6 out of 20, and then 5 out of 19. Second one would be 10 out of 20, 9 out of 19. 4 out of 20, 3 out of 19. And you would add each one of those up because they're separate probabilities, and you would add each one up. And you'd get your probability, which is about just over 33% chance. So if you did this in a given week, you would probably have matching socks to 1-2 days. Okay. I think we are done. Hold on, let's see. Hey, done. There is no homework for this section, I don't think. Maybe there is. But this is an option. This is optional. So if you made it through this video, thank you. I appreciate it. You did not have to watch this. The homework in this section is optional. It is not mandatory. But since you watched this video, you know. Okay. All right.